Specific heat of an adsorbed mobile monolayer. If the surface of some solid is maintained in a reasonably good vacuum, a single layer of molecules, 1 molecular diameter thick, can form on the surface. The molecules are then said to be adsorbed on the surface. The molecules are held to the surface by forces exerted on them by the atoms of the solid, but they may be quite free to move in 2 dimensions on the surface. They form then, to a good approximation, a classical 2-dimensional gas. If the molecules are monatomic and the absolute temperature is T, what is the specific heat per mole of molecules thus adsorbed on a surface of fixed size? So using equipartition theorem, we can write for the kinetic energy, these are monatomic molecules. So we have the mean energy per molecule will be given by 1 over 2 mvx square bar plus 1 over 2 mvy square bar. Let's assume that the surface of the film is the xy plane. Film surface I'm calling xy plane. And using equipartition theorem, I have equal contribution to the energy of amount half a kT from each independent degree of freedom. So I find that the mean energy per molecule is kT. Then the total mean energy will be equal to capital N times kT. Capital N is the number of molecules, and therefore I can find the heat capacity by taking the derivative of the total energy with respect to T. It will be equal to Nk. But if I have 1 mole, so for 1 mole of the material, I have N is equal to Avogadro's number, N sub A. Therefore, the heat capacity will be NAK, which is R. So remember, R, the universal gas constant, is the Avogadro's number multiplied with Boltzmann constant. Or I can say that this is the specific heat because it's heat capacity per mole. C is equal to R because it's the heat capacity of 1 mole. So that is the molar specific heat. We could also define it per gram, remember, but here we are asked to find the heat capacity of 1 mole, which is the molar specific heat. So we have used equipartition theorem because the molecules are free to move in 2 dimensions and it's a monatomic molecule. So we can think about the translations of the translational kinetic energy of the center of mass of each atom. That's the only contribution. So basically I'm neglecting interactions between atoms, so that's why it says free to move in 2 dimensions. So the contribution is half a kT from each independent degree of freedom, so kT per molecule. N times K is the heat capacity. For N equals Na, Avogadro's number, we have 1 mole. The heat capacity is R, or molar specific heat is R.